This is the video for section 7.1 notes, slides 8 and 9, but we're starting on slide 7 just to jump off of there. All right. So slide 7 asked us to estimate the area under the curve y equals x squared from 1 to 5. And so we basically came to the realization that if we use more and more rectangles, we are likely to get better and better estimates. Right? And so the idea was, well, okay, so how are we going to get better estimates if we use more rectangles? Well, remember, the more I minimize this overestimate here, I'm going to get closer and closer to the true value. So the question then is, well, how can we get the true value, right? It's not geometric, right? This is a curve. So that's really what we hope to accomplish here. All right, so let's take this picture on slide 8. All right, now I'm starting at 1, right, and we're going up to 5. But you'll notice that I don't actually complete this, right? So yes, I'm showing you 5 rectangles here, but really what we're talking about is using any number of rectangles. So let's just say n rectangles. Okay, so we're using n rectangles, and then, if we say we want to use 4 or 5 or 6 or whatever, then we're kind of just going to insert, that number in for n. Okay, so now, first of all, okay, if we're going from 1 to 5, right, that means we have a width of 4, right, to split up among n rectangles. Okay, now each particular rectangle we're going to say is this. We're going to call it delta x, or change in x. All right, and so delta x, the change in x from one rectangle to the next, is actually just 4, the total width, divided by n, the number of rectangles. All right, so that's what we're going to be using as we go. So if I wanted 4 rectangles, I would say 4 over 4, right? So then delta x would be 1, like we did on slide number 7. Okay. If I wanted to use, 8 rectangles, then we would put 8 in. 4 over 8 is 1/2, right? So that would mean that each rectangle would be 0.5 wide, and so on. Okay. All right. So now what we want to do is we want to think, okay, if this is delta x wide, well, then so is the next one, and so is the next one, and so is the next one, and so on until we get to the last one, which is also delta x wide. They are all the same width, right? All right. So now what we want to do is we want to think about, okay, so if this rectangle is delta x wide, how tall is it? Okay, so what you want to notice here is I'm using circumscribed rectangles. All right, and it actually doesn't matter. Okay, you'll ultimately see, but we're going to use circumscribed rectangles. So let's say I'm going to put these points here. Okay, now each one of these points represents the x, y that gives you that point, right? And the y value is going to give you the height. All right, so now we need to think. All right, I'm starting at 1, right? So now, what is the x value when I started at 1 and I went over by delta x? It's actually just 1 plus delta x, isn't it? And so that means this point is 1 plus delta x, comma, well, now what's the y value? It's actually just whatever the function is, f of 1 plus delta x. Now remember, delta x is a number, right? It's just 4 divided by the number of rectangles, all right? So what does that mean? Well, that means the height of this rectangle, the first rectangle, is f of 1 plus delta x. All right, so now what are we going to do? We're going to take the area of this rectangle plus the area of this one and this one and this one and this one and so on until we get to 5, all right? So what does that mean? So I'm going to take the area of the rectangle, which is the width, delta x, times the height, which is, remember, the y value, so that'd be f of 1 plus delta x. All right, so that's the area. Then what are we going to do? We're going to add to it the area of the next rectangle. So what's the area of the next rectangle? Well, once again, it's delta x wide times the height. So now we need to think about that point. What is that point? Well, I started at 1, I went over delta x, then I went over another delta x. So that's going to be 1 plus 2 delta x's, right? So that means the next point is 1 plus 2 delta x comma, f of 1 plus 2 delta x. And so f of 1 plus 2 delta x is the height. So the second rectangle is going to be delta x wide times f of 1 plus 2 delta x. Okay, now in the first one, we could actually consider that there's like a 1 delta x there. All right, then we're going to add to it the area of the third rectangle. So the third rectangle is delta x wide. All right, but what is its height? Well, once again, we want to think about this point. What is that point there? It is, well, the x value started at 1, went over 1 delta x, then another delta x, then another delta x. So that point is 1 plus 3 delta x. So that means the x value is 1 plus 3 delta x, comma, and the height would be f of 1 plus 3 delta x. And so the width, once again, is delta x times the height, which is f of 1 plus 3 delta x. And so we're going to continue on. Now we're going to find the area of the fourth rectangle. Well, what's the area of the fourth rectangle? Well, they're all delta x wide. So now, notice the pattern. F of 1 plus 4 delta x, and then 5 and 6 and 7. So we say plus and so on until we get to, well, what we're going to do is we're going to go all the way to the end, right? So the last rectangle is going to be the nth rectangle. So once again, it's going to be delta x wide. And what is its height going to be? Well, when we get to the end, the height is going to be f of 5. But if we follow the pattern, it's going to be f of 1 plus n delta x. All right, and so now what the goal is actually to say, okay, well, how can we write that in a more succinct fashion? Well, what we're going to do is we're going to write it as sigma notation. We're going to say, well, this really represents the sum from k equals 1, right? We're going to start at 1 to n of what? Well, remember, all of them are delta x wide, so we can put delta x there, times the function f of, well, what's the function? 1, they all have 1, plus, so 1 plus. Here's where we're inserting k. 1, 2, 3, 4, and so on. So we would say k delta x. And so if we were to write out that expansion, that's what we have. Okay, so now, how does this fit into, well, this particular one? Well, we would actually want to think about the, the actual formula that we were looking at. All right, so what was the function that we were dealing with? Well, that was actually x squared. All right, and delta x we said was 4, specifically 4 because it's 4 units wide. So we would say, okay, well, this is the sum from k equals 1 to n of delta x is 4 over n times the quantity f of 1 plus k delta x. Well, delta x is 4 over n once again, right? But now remember, this is f of, right? So now we want to make that into our function. What was f of x? Well, f of x was just x squared. So we can say now that this is the sum from k equals 1 to n of 4 over n times the quantity 1 plus k times 4 over n, quantity squared. So now we would just have to calculate that for whatever the value of n is that we want. So if we said, okay, let's do 100 rectangles. So we put in 100 for n, and then we would do this calculation. Now, obviously, writing out the expansion is kind of tedious, right? And actually, for a large number like 100, writing out the expansion would be totally ridiculous. All right. So now what we want to do is we want to have a better way of approaching this. Okay. But here's the kicker. No matter what I do, I'm still going to have some overestimate, right? Even if I get really, really small, I'm still going to have an overestimate. So the question is, how do we find the exact area under the curve? Not an estimate, but the exact area. Well, the answer to that question is that we want to use, well, not, 4 rectangles or 10 rectangles or 100 rectangles or even 1,000 rectangles or 1,000,000 rectangles. We want to use an infinite number of rectangles. So how do we do that? Well, let's talk about what we started with, right? We started with the sum from k equals 1 to n of delta x times f of 1 plus k delta x, right? That's what we started with, okay? Now, what did we say we wanted to do? Well, we wanted n, the number of rectangles, not to be like just, kind of large, but we want it to be infinitely large. And so what we're actually going to do is we're going to evaluate the limit as n, not x, as n approaches infinity. So we're going to treat the sum as if n is some unspecified constant, and then we're going to evaluate the limit as n approaches infinity. And so what this is going to do is find for us the exact area, not an estimate, the exact area under the curve. All right, and so what we want to do is we want to make it specific. So limit as n approaches infinity, sum from k equals 1 to n, and then we're going to bring back what we did on the earlier slide. So delta x, remember, was 4 over n, and then the function is x squared, so we're going to take 1 plus k times 4 over n quantity squared. So now remember, in terms of the sum, n is an unspecified constant, right? It's 4 or 10 or 100 or 1,000 or whatever, okay? N does not become the variable until we consider the limit, all right? And so now what we want to do is we just want to evaluate this summation. All right, so what do we want to do? So first of all, I'm going to expand this 1 plus k times 4 over n squared. All right, so I bring down the limit as n approaches infinity, and then I've got the sum from k equals 1 to n. All right, so I've got the 4 over n on the outside. Now, if I expand this, what do I get? Remember, this is really just 1 plus 4k over n times itself, right? 1 plus 4k over n. All right, so if I multiply that out, I get 1, right? 1 times 1. Then I get 4k over n plus 4k over n. Remember, this is like 4 is the coefficient. So there's 4 k's over n plus another 4. So there's actually 8k over n, right? So that's easy enough. All right, and then if I multiply 4k over n by itself, I get 16k squared over n squared, right? All right, so now what I want to do, in order to use some of the properties of summations, I want to distribute the 4 over n. So I get the limit as n approaches infinity of the sum from k equals 1 to n of, all right, so if I distribute, 4 over n times 1 is 4 over n. Plus, all right, 4 over n times 8k over n. So 4 times 8, of course, is 32. And then I have a k over n squared. All right, plus now if I multiply here, I get 4 over n times 16k squared over n squared. So 4 times 16 is 64. And then I've got the k squared and then over n cubed. All right, and so now I have the sum of those three things. So now, remember what we were doing yesterday, where we're taking this and distributing, or sorry, we're not distributing, sorry, we are separating into three separate summations. So now all of this stuff is inside of the limit. So I have the limit as n approaches infinity of. So now, first one, I have the sum from k equals 1 to n of 4 over n, plus the sum from k equals 1 to n of 32k over n squared. All right, then I have plus the sum from k equals 1 to n of 64k squared over n cubed. All right, so now three separate summations. All right, so now what we need to do is we need to think about more properties of summations. All right, so more properties of summations. All right, so the first one, okay, and this is one that people struggle with. What did I say n was? N is an unspecified constant, right? K is the variable of interest, right? The index. So if I'm plugging 1 in, I'm not plugging in for 1, I'm plugging in for k. Notice there is no k here. So actually, this is just a constant. So how does that sum behave? It's actually 4 over n, whatever that constant is, times n, right? In other words, just 4, right? Think about it. I would be taking 4 over n plus 4 over n plus 4 over n plus 4 over n times. Okay, now plus the next one. All right, I've got 32k over n squared. But once again, 32 over n squared, that's a constant. So I can bring that outside. So I have 32 over n squared. Then I have the sum from k equals 1 to n of just k, right? And in the same way, the next one, I have the 64 over n squared. Remember, n is an unspecified constant. So 64 over n squared can come out, and I'm left with the sum from k equals 1 to n of k squared. Okay, so now this is something that trips up a lot of people. N is not the variable of interest in the summation. It is the variable in the limit, which we are not touching until we deal with the summations. All right, so now let's simplify a little further. The limit as n approaches infinity of. All right, so now 4 over n times n, we said that's 4. Okay, easy enough. Plus 32 over n squared. Now, the sum from k equals 1 to n. We talked about this yesterday. If it is of just k, remember, what does that sum equal? It equals n times n plus 1 over 2. plus the next one, 64 over n squared. Remember, we talked about the sum from k equals 1 to n of k squared. Remember, that is n times n plus 1 times 2n plus 1 all over 6. Right? All right, so now I dealt with the summation. So now I'm left to evaluate the limit. All right, so first of all, I have the limit as n approaches infinity of 4, right? Okay, well, that's just 4, right? There's no n with it, right? So 4 plus. All right, now I have the limit as n approaches infinity of, okay, if I think about this, if I were to multiply this out, I get n squared plus n, so times 32, so 32n squared plus 32n, all divided by 2n squared, right? And then plus, now I'm going to deal with that in a minute. All right, so I have 4 plus. Think about this, okay? If I'm evaluating the limit as n approaches infinity, now n is the variable of interest, so now how does this behave? Well, remember, okay, we can divide everything by the highest power, so the highest power is n squared, right, is 2. And so if I divide everything by n squared, I'm going to be left with 32 plus 32 over n plus 2, or sorry, divided by 2. And so that means when I plug in infinity now, I get 32 plus 0 over 2. In other words, 16. All right. And then lastly, same thing. But now, if I multiply the n times n plus 1, of course, I get the n squared plus n. And then distribute again, all right, I'm going to get 64 times 2, so 128 n times n times n, so n cubed, right? And then plus, yes, some stuff with n squared, some stuff with n, some stuff with, a constant, whatever. I don't really care about all that stuff. Because take a look, my where is it? My denominator should be n cubed. I apologize. N cubed, and so in the denominator I have 6n cubed. You'll notice the n cubed is the same on top and bottom, and so once again we're going to divide by n cubed, and we're going to end up with 128 over 6. So 128 over 6, and now you'll notice there's no variables left. And so what is the exact area under the curve? Well, it is 4 plus 16, so 20 plus 128 over 6, which of course reduces. So I have 20 plus, they're both divisible by 2, 64 thirds. So this is 60 thirds plus 64 thirds. So 124 thirds, right? Or 41 1/3. And so that means that the exact area under the curve y equals x squared from 1 to 5 is 41 1/3. Not an estimate. This is the exact area. All right, so now just to take a step back, okay? If you have any function, we'll call it f of x, all right, on an interval a to b, okay, the width of a rectangle, delta x, is going to be b minus a over n, right? That's how we got the b minus a. That's how we got 4. We're going from 1 to 5, all right? And so then you are going to evaluate the limit as n approaches infinity of the sum from k equals 1 to n of delta x times f of a, right? We started at 1 because we were going from 1 to 5, plus k delta x. So you can apply this in order to solve problems 16 through 18.